So dear students, so today we are going to study the formation of PN junction and its biasing, that is forward and reverse biasing of a PN junction. Now the PN junction is very important for any semiconductor device because all semiconductor device having one or more than one PN junction, and the working mechanism, the physics of the semiconductor device entirely depends upon the property of the PN junction, that means how the PN junction behaves. So let's investigate what is PN junction, how PN junction is formed, and if we apply external voltage, then how that PN junction will respond to the applied bias voltage and what will be the current flow through the junction. Now a PN junction is formed when let's say we have a piece of semiconductor and one side is p-type doped and another one side is n-type doped. Okay. So that and this region, the mid portion, so we can say this is the junction region. That means so this imaginary line separates the p region with the n region, and let x equal to 0, that is the junction point. Okay. So one side is acceptor type doped, that means here in this side the holes are the majority carriers and in the n side electrons are the majority carriers. Okay. Now, another one thing, when you are applying doping, so depending upon the doping profile, how the doping varies, so there may be two types of junction. So number one, it is called step junction or step graded. Okay, and number two is a linearly graded junction or linearly graded junction. Now, what is step junction? If the doping concentration suddenly changes at the junction, suppose here at x equal to 0 point, if the doping concentration, suppose this is my x equal to 0 point, at doping concentration suddenly changes from p to n, that means if I plot the graph, if the graph looks like this one, okay, so before x equal to 0 it was a p and having a constant doping concentration, and suddenly it changes to let nd, and here it is na, acceptor type and donor type. If suddenly it changes like this, okay, so then this type of junction is called step graded junction because it looks like a step. But for linearly graded junction, the situation is like this. This is my junction region, this is P region, this is N region. If the doping concentration varies linearly, means slightly like this, okay. So then we can say, so this type of junction is called linearly graded junction, or maybe like this. Just a minute. It maybe okay. Just like this. Okay, that means see here the doping profile changes abruptly, but here doping profile changes linearly. So of course it's very difficult to achieve this type of junction, and it's just a theoretical concept, and practically it is difficult to achieve this type of step graded junction. So almost all PN junctions are a linearly graded junction. Okay. Anyways, so basically for analysis purpose, when we are going to derive something, so we consider it as a step graded junction, because using the step graded junction, that formulation and derivation will be much more easier compared to linearly graded junction. Okay. So here in this video we are not going to derive anything, just we are going to explore the theoretical aspects of PN junction. So let us see. So when that P region and N region is formed, then what to expect, then what will happen? Okay, now see one interesting thing, that in the P side, since the holes are majority carriers and N side electrons are the majority carriers, so there is a variation in concentration. So what I'm saying, that see, okay, in P side the holes are the majority carriers, but in N side minority carriers are holes. So there is a variation in concentration or concentration gradient of hole. Okay, so this is P side having higher hole density, N side having lower hole density. Similarly, just opposite, that is N side having higher electron density and P side having lower electron density, because the majority carriers are electrons at N region and majority carriers are that minority carriers are electrons in P region. So of course there will be a diffusion, because whenever there is a variation in concentration, that is concentration gradient, so there will be a diffusion. So now holes will diffuse from this P side to N side, and electron will diffuse from N to P side. Okay, just opposite direction. So now question is how long this diffusion process will continue. Okay, so whether it will continue for infinite time, or let us see what will happen. And what will happen when this diffusion process will continue. Now when the diffusion process will continue, as you know that when holes are moving, it left some negative ions. Okay, so why negative ions? Again, go back to the formation of p-n junction, p-type semiconductor. Suppose boron, we are adding trivalent impurity, so it is having 3 valence electron, and one electron added forcefully to complete the covalent bond structure. Okay, and one vacancy is created, so that vacancy is treated as hole. So boron having valency 3, okay, one extra electron is added, so it became B minus ion. Okay, so when the hole is moving, the diffuse from P to N side, so it left some negative ions. Okay, so it left some negative ions. Okay, like this. So those are negative ions, and of course they are fixed. They are not mobile. They are immobile or fixed. Okay, some negative ions are there. And the same thing happens when electrons are moving, the diffusing from N to P side, they left some positive ions, because that phosphorus having valency 5, out of 5 valence electron, 4 are inside covalent bond, so 1 behaves like free electron. So you are taking 1 electron from phosphorus, so it became P plus. Okay, so in the N side, the positive ions are generated, and of course they are fixed, they are not free. Okay, this one. Now the question is why the ions are present in that near the junction region. Okay, that means why initially that the ions are deposited near the junction, why not at this position or at this position. The reason is, so we know the diffusion force, or whatever the rate of diffusion, that is directly proportional to, so the rate of diffusion, that is directly proportional to concentration gradient, and concentration is gradient is nothing but del n by del x. Okay, so when you are moving away from the junction, what will happen? The dx parameter, this parameter will increase. Okay, as a result, the rate of diffusion, the dn by dx term will fall, and rate of diffusion will less. So the holes and electrons, those who are present near the junction, okay, so they will diffuse first, because in that case the dx is very small, so concentration gradient will be very high, and the rate of diffusion will be higher. Okay, so the majority carrier electrons and holes, those who are present near the junction, they will diffuse first, and that's why the depletion layer, that is those fixed charges, are deposited near the junction. And we can give one name, the name that's due to the presence of this fixed positive and negative ions. See, one layer is created, okay, which contain no free charge carrier. All charges are fixed. Those are ions. They contain positive and negative ions. Okay, all those are charged, but they cannot conduct current because they are fixed. They are not free. Current conduction is possible when there is a free carrier, not fixed. Okay, but those are fixed carrier. Okay, so they create the layer, so this is called the depletion layer. The name of this layer is called depletion layer, or depletion region, or we can give depletion region, or space charge region. So those are different name of this region: depletion layer, depletion region, or space charge region. Okay. Anyways, so now it is clear that when the holes or electrons are moving, so depletion layer will be created. So how long the diffusion process will continue, whether this whole P region will be filled by negative ions, or this total N region will be filled by positive ions, or it will continue up to some time. So let us see what will happen. Now see, when gradually the depletion charges are deposited near the junction, that means see at N side the charges are positive. Okay, the depletion charges are positive. So now when one hole is trying to move from P side to N side, so it faces the depletion charge in the N side. See, it faces the depletion charge in the N side, which is positive in nature. So it will repel that hole. Okay, so it will repel that hole. The same thing is true when the electrons are diffusing from N to P side. So the depletion charges, that is the negative ions here the negative ions present in the p side, those negative ions will repel the electron because they are same type of charge carrier. Okay, so they will repel the electron. So initially there was no that positive and negative ions, so there was no such repulsion force. But now gradually when the charges are built up, the depletion layer is formed. So this repulsion force magnitude will increase, and when this diffusion force, okay, suppose if we are talking about hole, so the diffusion force acting in this direction, holes will try to diffuse from p to n side, and the repulsion force, okay, is acting on hole in just opposite direction. Okay, so due to the presence of those positive ions, the hole will be repelled back into the p side. So when the magnitude of this diffusion force and repulsion force, okay, will be exactly same, then there will be no such further diffusion, and we can say the structure is in equilibrium. The same thing happens for electrons. Okay, when this diffusion force and this repulsion force, the repulsion force is coming due to the presence of fixed ions. Okay, or sometimes we can say this is the electric field force, because whenever the charges are there, there will be electric field force. Okay, so the repulsion force and electric field force, okay, will cancel each other. So then we can say, so there will be equilibrium condition and no further diffusion will happen. Now the p-n junction is in equilibrium. So what will be the band diagram? Because we can explain so many things from the energy band diagram. So similarly, if we want to draw the energy band diagram under this condition, that means when the p-n junction is in equilibrium, then what will be the shape of the band diagram? So let us see. Okay. So energy band diagram of unbiased. Why unbiased? Because till now we are not applying any external voltage. p-n junction, energy band diagram of unbiased p-n junction. So let us see. So how to draw the energy band diagram? One side is p type, another one side is n type. So how to draw it? Now you first, since the structure is in equilibrium, the Fermi level for both p and n side, it is in the same level. Okay, the Fermi level will be constant throughout the system. So Fermi level will be constant throughout the system. Okay, so this is our p side, this is our n side. Okay, now with respect to Fermi level, you draw all other position of energy band lines, that is conduction band, valence band, and intrinsic level. Now this is p side, p-type semiconductor, and you know that the position of Fermi level will be near valence band. So if the Fermi level position is here, then we can say the valence band will be somehow here, EV. So EV stands for valence band, EF stands for Fermi level. If the valence band is here, so conduction band will be definitely, okay, away from the Fermi level. This is EC. So this is the situation for p-type semiconductor. Now if we draw the same thing for n-type semiconductor, for n-type what will happen? The Fermi level, okay, is near conduction band. So position of conduction band will be here, because Fermi level, we are not shifting Fermi level. The equilibrium is achieved and Fermi level is constant throughout the system. So this is conduction band, and the whole semiconductor is the same type of semiconductor, means p region or n region, but the semiconductor is same. So their band gap, the distance between EC and EV, it is same. So you have to maintain the same distance between EC and EV. So p side is also silicon, n side is also silicon, for example. So the band gap of silicon, that is same. So by applying doping, you cannot change the band gap value. Okay. So this is for the situation for n side, because the Fermi level near the conduction band. Now if we draw the intrinsic level position, so you can draw it. Intrinsic level will be at the mid position. So this is EI. This is also EI. Now let's join all those lines like this, and here the EI level will also be joined like this. So this is the band diagram of a p-n junction, unbiased p-n junction. Remember, we are not applying any external voltage, unbiased p-n junction under equilibrium. So we can explain so many things, so different phenomena from this energy band diagram. Now see, in the energy band diagram, the energy increases in the upward direction. That means when you are moving in the upward direction, the energy of electron will increase. Energy of electron will increase. Okay. So now see, now if you want to transfer, because this side is n side, I already mentioned. So if you want to transfer one electron from n side to p side, okay. Now see, the free electrons are there in the conduction band. So if you want to transfer electron from n side to p side, so you will face one barrier. Okay, the height of the barrier is this one. Okay, see, if you can apply this much amount of energy, then you can transfer the electron from this side to this side. Otherwise, you cannot transfer the carrier. And when there is no transfer of electron, so of course there will be no current. Okay, because due to the you are getting the current due to the movement of electron or hole. Okay. So in the equilibrium, see, we are not getting any current basically. Okay, if we neglect the leakage current, okay, so then at the unbiased condition, zero biased, we are not applying any bias voltage, so there will be no current in the system. Okay, due to this basically, due to the barrier height. So this barrier height is called the VBI. Since we are working with the band diagram, so all energy unit will be in the electron volt, E into VBI or Q times of VBI. So VBI is the built-in potential barrier or simply barrier potential. So the barrier height faced by the electron in the n side. So if you want to transfer electron from n to p side, so you have to apply at least this much amount of energy. Okay, you have to overcome this barrier height. Okay, so this is. So now come to the forward bias and reverse bias condition. So what is forward bias and what is reverse bias? So forward biasing of PN junction. Now see, the forward biasing and reverse biasing is already familiar to you, and from the basics you know that the forward biasing means if we apply a positive potential at P side and negative potential at the N side, so then it is forward bias and there will be current in the PN junction. Okay, some current will flow, you will get some current. So we can explain all those things from energy band diagram in a more physical way. So actually what will happen? Okay, see, again, let's draw the diagram, okay, quickly, without drawing details. So this is the conduction band, this is the valence band, this is P side, this is N side, this is conduction band, and this is the valence band at unbiased condition. Okay. So when you are applying a voltage, we will work with the electron only because it's easier, much more easier to explain the phenomenon by using electron. Okay. Now see, at the N side you are applying what? Negative potential. So you are applying a negative potential here in the N side. So electrons are negatively charged. You are adding negative potential at the N side with respect to P side. Then what will happen? You are adding more negative potential. So energy of electron, definitely it will increase. So electron energy will increase means now the conduction band will shift. Let us see this one. Now the conduction band will shift what? In the upward direction, because you know that energy increases in the upward direction. Okay. So when the conduction band shifted in the upward direction due to the application of this bias voltage, okay, so valence band will also shift. So why valence band will shift? Because the band gap is constant, the distance between EC and EB, it is constant. So at unbiased condition, position was here and here. Now it is shifted to this one. Now this is the new position of valence band, this is the new position of conduction band. Now see, previously the barrier height was this. Now the barrier height reduces. Now if you increase this bias voltage, let VBB, if you further increase this one, then what will happen? Ultimately this barrier will vanish. Okay, this barrier will vanish, and now the electron from N side can easily flow to the P side. So the electron from N side can easily flow to the P side. That means now you will get the current in the circuit from P to N side, because the direction of current flow and direction of electron flow, that is just opposite. And since the barrier height reduces, so this is nothing but the forward bias. So in forward bias, the barrier height of electron reduces. And what about depletion layer? the depletion layer that was present near the junction, the thickness of a depletion layer reduces. Okay. Now coming to the reverse bias phenomena. So let us see what is reverse bias. We can explain in the same way. So reverse biasing of PN junction. So reverse biasing means if you just change the polarity, so you have a PN junction, if you change the polarity means P side connected to negative terminal and N side connected to positive terminal of a battery. Then it is called reverse bias, and we are saying that the current will be zero theoretically. Practically it's very small, negligible amount of current will flow. So why? What is the reason? Again go back to that energy band diagram. Again this P side, conduction band, valence band, and this N side, conduction band, valence band. So this is the situation for equilibrium case. So now see the N side we are applying what? The positive potential. Okay, so here this side we are adding positive potential at which side? The N side. Okay, so electrons are negatively charged, you are adding positive potential, so energy of electron will fall, energy of electron will reduce. Then what will happen? The electron energy reduces means in that energy band diagram, energy reduces means the band will shift in the downward direction. Now the new position of conduction band will be here, and the new position of valence band will be here, because the valence band will also shift in the same way. Ultimately the band gap, the distance between EC and EV, that is constant, that is equal to band gap. So if conduction band will shift in the downward direction, the valence band will also shift in the downward direction. Now see, previously the barrier height was this one, now the modified barrier height is this, so barrier height increases. Okay, so barrier height increases, so this is called the reverse bias. And due to this increased barrier height, so it is difficult to cross this barrier. Okay, so without crossing the barrier, so no carrier can move from N to P side, so here you will not get any current. Okay, so the current is zero. But in practical cases, due to the temperature effect, a negligible amount of current will flow. I will explain why you will get the current in reverse bias. So from this diagram we are getting zero current because no carrier can cross the barrier. Okay. Now what will happen to the shape of depletion layer? So here you are applying negative voltage. So negative voltage, what will happen? All holes are attracted towards this terminal due to this negative potential, and similarly electrons are attracted towards this terminal due to this positive potential. So as a result, what will happen? So more number of negative ions will be generated here, because if all free holes are attracted towards this point and all free electrons are attracted towards this point, so more number of negative and positive ions are generated near the junction. So the thickness of a depletion layer will increase. So the summary is, in reverse bias, the depletion layer thickness increases, and forward bias, depletion layer thickness reduces. This is the first thing. And mathematically we can say the EVBI is the barrier height at zero bias. Now in forward bias, so we can say the barrier height reduces. Okay, so the expression is something like this: E into VBI minus VF. VF is the applied voltage, forward voltage we are applying, and the reverse bias, it will be just like E into VBI plus VR. Again VR is the applied reverse voltage. Okay, so barrier height increases in reverse bias, barrier height decreases in forward bias. Okay, so this is the expression for this. So now why will get current in reverse bias? Why a small amount of current will flow in reverse bias? So let us see that thing. Okay, so leakage current, we are giving one term, leakage current in reverse bias, PN junction. So what is the origin of leakage current in reverse biased PN junction? Let us see that thing. So we have a PN junction, it is in a reverse bias like this, so minus plus, so it is connected to minus, this is connected to positive terminal of a battery, VBB for example. Now see, Due to the temperature effect, if some of the electron hole pairs are generated, because see, some of the covalent bonds are broken, and that happens in room temperature also. So some of the EH pairs are generated. So electron hole pairs are generated throughout the semiconductor. Okay. Then what we can expect, see. So this terminal, so here this side we are applying what? The negative. So of course the generated holes, okay, they will move towards this, because this potential this side is negatively connected to negative terminal of the battery, and so holes are attracted towards this, the thermally generated hole. And similarly, the thermally generated electrons in the structure, okay, those who are generated due to the temperature effect, okay, the thermally generated electrons in the structure, they will move what? Towards this. So the electrons will move towards this. Okay, so electrons are moving towards this. Okay, and holes are moving towards this. So ultimately in reverse bias also you will get a small amount of current, because the current you are getting, that is entirely due to this thermally generated carriers. Of course they are very small in nature, so the current you will get in the reverse bias, that is very small, negligible amount compared to the forward bias. So if we plot the graph IV characteristics, so this is the applied voltage and the current. So first quadrant means voltage is positive, and a forward bias that indicates, okay, and show the forward bias graph is like this. Okay, so up to some value of forward bias the current will be negligible, because you need to cross this potential barrier we already discussed now. So in a forward bias also, so you need to apply minimum amount of voltage to show that that potential barrier height will be negligible. After that the current will start. Okay, so here we are getting the same. So this voltage is called the V gamma, or you know the term that is called knee voltage of PN junction. And reverse bias, the current is very small, it's close to zero, and after some value of reverse voltage, okay, and there will be breakdown. So we'll discuss this term later. So this is VBR. So this is called the breakdown of PN junction. So we shall discuss it in some other video. It's called the breakdown region. So this is the forward bias region. This is the reverse bias, means this quadrant. Reverse bias region, so it is minus P, it is plus P. So the graph you are getting, so that is basically exponential characteristics, and this is basically the VI characteristics of PN junction diode. So today up to this. Thank you all.